Hi, good afternoon. My name is Kaushik Datta. I am the quantum research lead at Noblis. We are a science and technology company just down the road in Reston, and we support agencies all across the federal government. Today I'll be talking about creating new quantum algorithms for real-world impact. And so this is my self-assessment of quantum computing at this point. So quantum error correction seems like it's moving forward. Google has made an announcement saying that they've achieved some milestones so that they exponentially decrease error with the number of qubits. So, it's moving in the right direction. This might be a little bit optimistic. Qubit scaling looks like it's moving in the right direction. Different companies are thinking about how to go off chip and introduce modular architectures so that they can keep scaling. But really, where are the quantum algorithms that can help move quantum computing forward? So that's something where I'd like to talk about today. We need more quantum algorithms that solve problems efficiently compared to classical algorithms. So to underscore this point, a couple of years ago, a paper came out that talked about the likelihood of quantum advantage. And what they did is they compared a current GPU, one of the NVIDIA high-end GPUs in 2023, versus a very optimistic future quantum computer. And the real limitations were, one, getting data in and out of the quantum computer is very expensive. So the I/O is really an issue. So you really have to focus on small data problems. Big data problems in quantum computers seems very much out of the picture, at least at this point. And two, we've had decades of Moore's law. So, the doubling of computing power every 18 months for many decades. Classical computers are really well designed to do computation, and they are orders of magnitude faster than any future quantum computer in that regard. So unless you have exponential quantum speed up in your algorithm, you really don't have a shot. So, the two use cases that they really talk about as, possible for getting quantum advantage, not definite, just possible, are quantum system simulations, chemistry, material science, what Richard Feynman suggested initially when he wanted to talk about quantum computers, as well as Shor's algorithm for integer factoring and breaking cryptography. There isn't a lot more at this point that really even has a shot of being a good candidate for quantum advantage, and that's where we want to focus. So what are the other practical quantum algorithms? So, the plus side for quantum computing is that qubits can be manipulated in many more ways than just bits, which can just be up or down. So here, we have this animation where we apply a Hadamard gate to this qubit and it puts it into superposition. Then we have a phase angle shift, a Z gate to rotate it. So, that's obviously well beyond what any single classical bit can do. And of course, if you entangle multiple qubits together, you get, 2 to the n basis states, and you have, a lot more computing power in a general n-qubit quantum state than a possible n-bit state. But of course, when you go to measure it, you read out just bits, not qubits, because the quantum state collapses. So, even though you have many more ways to manipulate and can store more information, ultimately you're just reading out bits. So currently we are in the NISQ era of quantum computing, noisy intermediate scale, but that should not stop us from doing algorithmic innovation. Really it's challenging to work with real quantum computers at this point because of the NISQ era. And so, what I propose, and I think many of you in the audience probably agree, is that, we should really try to leverage quantum simulators as much as possible that run on classical machines. The tensor networks that underlie these quantum simulators are improving rapidly. Right now on a laptop, you can probably simulate up to 20 entangled qubits. On a supercomputer, more likely 40 qubits, but potentially 50 if conditions are right. So, our long-term holistic vision for quantum algorithm development really focuses on, one, being data-driven, two, trying to look at fault-tolerant, not NISQ algorithms, although we can fine-tune it for current-day machines, and optimizing across the entire algorithm, and just trying to get a deeper understanding of what works and why, so that we can create better feedback loops. So this is the high-level plan. This is just something that I thought would be a useful template. This is not, a catch-all for all types of quantum algorithm development. This is certainly not the approach that Shor took for cryptography. But, first focus on a small data problem of interest, because we know large data problems will not work, or we highly doubt that they will. Gather or generate an abundance of problem-specific data. So if you have some sort of data generator for that problem, leverage that. Use quantum simulators to develop an algorithmic testbed. Create new algorithms. Look at both hybrid as well as purely quantum methods. Vary how the problem is encoded, and develop sensible optimizations. And we'll talk about some of these in a moment. Efficiently explore that space of quantum algorithms to identify the best ones and validate these algorithms. And interestingly enough, only 6 requires a real quantum computer. So there's a lot of legwork that you can do without any real quantum hardware at this point, given some of the drawbacks of currently using quantum computers. So the goal is to develop a higher level intuition about what works and why. So how many of you know about a website called Kaggle? Right. So I would imagine that many of you are data scientists or work in the data field. They give you data sets from different organizations, and machine learning experts from around the world, the top machine learning experts in the world, go there, and they have a problem-specific data set. Part of it is public, part of it is private. So you can submit your machine learning model to the website, and you get instant feedback using some sort of performance metric to see how well you match that data set. So the quality of a model is quantified by that performance metric, and the testbed allows for fast iterations. So what I'm proposing, and I don't know if this is a new concept, but a data-driven quantum algorithmic testbed. So here, instead of having a machine learning model, we take a quantum algorithm, stick it into a noise-free quantum simulator. Probabilities are extracted using the Born rule. And we take that same data set and we output a performance metric. So this is a simple way to just get a quantified way of saying how good or bad an algorithm is. And so we can use HPC methods to try out lots of different algorithms and see which ones are actually effective at the problem at hand. And so some of this comes down to how we encode problem information. It really varies depending on what types of data that you're working with: scalars, vectors, images, constraints within the problem. MaxCut is probably one of the first programs that people write when they write quantum algorithms, and it's very well suited to quantum machines because each binary variable is a qubit. But you could potentially take a qubit which has an infinite number of states and map the traveling salesman onto it and solve that on a single qubit, as people have done in a paper last year. So I'm not saying that's the best way to encode that information, but it is a possible way to do it. So, we need to explore how best to encode the information onto a set of qubits to see which ones get the best results. Once we do that, we choose the space of algorithms that we want to look at. So we try to come up with optimizations, exploiting structure in the problem, leveraging subject matter expertise. I will not kid you, this is not a mechanical process. There's a lot of subject matter expertise here, and it requires a lot of deep thought and understanding of how quantum computers work. But this is my proposal for how to approach this problem of creating new algorithms. So we take optimizations, we choose reasonable parameters for each, and we expose those. And one that we have found that seems to work for WTAP, the weapons target assignment problem, is, actually reducing the amount of data that we put into the algorithm. So we took the state-of-the-art algorithm for solving this problem, and we took out the least valuable targets, and we saw that, for problem sizes of interest, that upper right red square, we actually get 27% improvement over, the state-of-the-art. So, you have to be thoughtful about which optimizations you expose, but you could certainly do better than a lot of what the publications that are out there now. And then how do we explore this large algorithmic space once we, expose all our parameters and we try to search it? There's a lot of techniques out there. Simulated annealing is one. Reinforcement learning is another, where you have trial and error methods, and you see, where you have better reward functions, random search potentially. But ultimately, what we're trying to do is get a better grasp as to how we can tighten that feedback loop, so we know we're going in the right direction and getting better algorithms over time, potentially using machine learning methods. So I apologize, this is a high-level talk. I wish I had more results to show here, but this is just building our intuition as to what works and why. And then how do we validate the chosen algorithm? So, the traditional method here is using quantum simulators, again, with noisy models to replicate, how different qubit modalities would operate, and then, potentially choosing one or two of those and then running it on the real hardware to confirm that, the noise models were correct, that we're seeing the same results. Here, finally, the number and types of gates play a role. So, obviously with the noise-free simulator, you could have a huge depth of the circuit and it wouldn't really matter. Here, you actually can figure out, which gates are, how gates impact your circuit. So the takeaways here, I have real concerns, and I think a lot of people do, is that the lack of quantum algorithms may hinder adoption of quantum computing because it is just really hard to beat classical machines. And, unless we try to innovate and try to come up with better quantum algorithms, this will be a sticking point going forward for the industry. We need to leverage quantum simulators and subject matter expertise to understand which encodings and optimizations work and why, and leverage these insights to create newer, better algorithms. And then we leverage HPC techniques. Like each time you try an algorithm, that is embarrassingly parallel. So, you can scale this up on GPUs or parallel machines and see which algorithms work and get your results faster so you can continue innovating. And of course, this should be augmented with theoretical algorithmic research for deeper understanding because, that obviously is key as well. So we need to apply all our resources to finding the needles in the haystack. Here are the references that I talked through in the presentation, and thank you very much.